So, I think you guys are experts on this, but we're gonna go over the notes and the descriptions of Newton's third law. So Newton's third law says every action has an equal and opposite reaction, or every force has an equal and opposite force. I pushed on Brian with 20 newtons. He saw 20 newtons on his scale. How much did I see? No, I didn't see that. Sorry, it was 20. It was 10 after I let go. And he would see 10 just after he was letting go. But what I would see just as I was pushing on it? 20. So anytime you interact with our surroundings, we feel that third law. You hit somebody, you apply a force to their face with your hand, so their head kind of turns or it squishes. But their face also applies that same amount of force to your hands. Since the face is softer than your hand, it suffers more from the interaction and deforms more because it's softer. And this is important, it's like space travel. Because there's no friction in space. Like cars use friction to get around between the tires and the road. If there was no friction, the tires would just spin. So when you go in space, they shoot out jets of gas and steam. And so they're pushing out steam or gases. In that direction, let's say. So if we're putting a force and pushing out gases on that direction, why does the spaceship move to the right? You can tell me if you, Francesca?
Every action has an equal and opposite reaction.
Okay, so what does that mean?
So like the force that's going that way is the same that going the opposite way?
Yeah, we're the rocket ship's applying a force on the gas to propel it that way. What is the gas doing? Applying force that way. Now, does the gas move out as fast as the spaceship flies, or faster? Faster. Why?
Because like when you push on it, it was like
Yeah, it has. Gas has much less mass, so the gas will accelerate faster because of Newton's second law. But it's going to be the same, always the same force. Another example is if you are on a lake. So you're going to have to just follow in your notes. If you're like on a lake in a boat and you're right near the, this might not be in your notes. You're right near the dock and you decide, I'm going to just jump off the boat onto the dock. What happens? Carter? Yeah, the boat will move backwards, then you'll lose your boat. Why does the boat move backwards? Yeah, you're applying a force. In order to propel yourself forward, you're also putting a force backwards on the boat, which propels it backwards. And like we were doing yesterday, because there's not as much friction in that water, it kind of floats on top and allows it to move. What about when you're running? So some of you guys play track or run track. How do you run faster? You got to push the ground harder, and every time, the harder you push off the ground does what? What does the ground do to you as you push on the ground? It pushes back. If I'm going this direction, what direction am I pushing on the ground? That way. What direction is the ground pushing on me? That way, it's in that direction. How much is the force? Not how fast, as much force as I'm putting on the ground. why do I move forward and the ground stays relatively not moving? Yeah, the ground has much more inertia than I do. Also has more mass, so it wants to stay still. I want to stay still because I'm not moving yet. But once I push off, Newton's second law says the more mass, more force required. I am much less massive than the ground. You're much less massive than the ground. So you're going to move a lot faster than the Earth would.
Is that why things bounce?
Not. It's why they do bounce. There's the force pushing back up. That's also a lot of elasticity, elastic energy, and reaction. But yeah, very simple. Looking at the example problem, Bob is tired of pushing his van to the gas station. He has an idea, hey, it'll go a lot faster if I'm rollerblading than walking. Why don't I wear my rollerblades? So Bob gets into his rollerblades from the back of his van, starts pushing. When he pushes on the van with 100 newtons of force, what happens? The mom? Well, what does a van do?
The van doesn't move, then like he is pushed backward because the van is a lot heavier.
Okay, Newton's third law, what does that say? Equal and opposite force. So if he puts a force on the van of 100 newtons, what's the force the van puts on him? 100 newtons. He's on roller skates, so there's very little friction. So if he's getting pushed with like very little friction, also pushing back in that direction, and he weighs much less, he has much less mass, what's going to happen to him? Yeah. So for example,
Oh, wouldn't this be like sideways stairs like these?
what?
The rollerblades would just stop.
Well, he could, I don't think he did. So this is my van,
Pretty strange
Small van.
van.
okay? So I'm going to push on it. What's going to happen to me? Why?
Because
But I'm pushing all my force that way. Shouldn't I go that way? The force.
you have less mass.
That wasn't very hard. You could just jump off.
Plus, I'm not connected to this, so I moved back before that started to move back. And which law is that? Why would I move back before this moves back?
First.
First law, yeah. Because the force is applied to me, not to the car. Then it would apply to him and the shoes because the roller skates because like you're physically tied into them. So you're one thing with the roller skates, but since I'm actually not tied into this, if I pushed hard enough, I'd fly back and this would just kind of stay there. But once I flew back, what would happen to this?
It would start rolling.
It would roll what direction?
Forward.
Forward,
Forward.
because I'm going this way,
Yeah, so
and
it would go that way, this
and I'd
way.
end up pushing off, equal and opposite. I get pushed that way, it would get pushed that way.
So forward could take every direction.
That next example, explain why the man is being pushed back after firing his gun. Hey, Mom?
So what you shoot is the like force of like the this is the like small explosion inside of the gun.
A small explosion, what does that explosion do?
It like fires the gun out, but there is opposite reaction that like pushes back onto.
Yeah. So when you fire a gun, you're shooting out a bullet. Right as you fire, is the bullet moving? Like as you pull the trigger? No. Is it moving after you fire it? Like right after you pull it? Yeah. How fast?
Hella
Like really fast, which means it has a very large what?
Speed.
Acceleration. There's a large acceleration, little mass. It's going to move really fast, right? With a certain amount of force. That force being applied to that bullet is also equal to what? The force on the gun.
Yeah.
What direction is the force on the gun?
It's gonna go the opposite direction, so.
Opposite direction. So, if you guys have heard of recoil,
Yeah.
and that's what recoil is. Why doesn't the gun fly back as fast as the bullet?
Because
Okay, it's got more mass. So, and if you're holding it to your shoulder, you get lurched back. Like with handguns, I'm sure you've seen this in the movie, if you guys have seen Ride Along. What happens to Kevin Hart when he shoots the
I only
big
saw Ride
shotgun?
Along, so-
He gets like thrown against the wall. Okay, because he's so massive. Now that
So.
you need a really powerful shotgun to actually do that. My physics teacher's friend hunts, and he took his wife hunting. She wanted to go. He didn't want to take her, but he's like, okay, I'll take you. And she kept getting knocked back every time she shot it, and she was complaining about it. He was like, okay, well, next time you shoot it, lean against a tree. So she shot it and shattered her shoulder. Why did she shatter her shoulder? Carter?
Because after the gun pushes her back, there's no area for her to go, and all the force is gonna go into her body and the tree. The tree's not doing anything.
Yeah.
The tree was more than her.
So-
and it's gonna hurt.
Excellent. You guys all hear that? So all that force is going to try and push her back. Well, Newton's second law, and kind of it's always first law is always there, but Newton's second law says the more mass of the object, the more it's going to want to accelerate with the same amount of force. So, or the more force it takes to accelerate it. So the tree, not only is it really big and massive, it's also, you know, concreted into the ground basically. So is it going to move? No.
Was that really?
If you, who here has ever punched a tree? Okay. Does the tree really, does anything happen to the tree? Maybe a little bark, but like, do you dent a tree? No, because it's really dense, okay? So the tree's not gonna deform very much. So like if I punch this, it's pretty soft, it'll deform,
Whoa.
and I won't hurt, like, it won't hurt me very much, right? If I punch this desk, would that hurt? Yeah, punch a wall. If it's not drywall, you can punch through. But like this wall or the brick wall, metal wall. Don't try it home, but I'm sure if you've known or seen somebody who's punched a wall, they break their hands. Okay, so all that force goes into you and your bones and everything like that. And your bones are far less dense, and they're lighter and smaller than that tree. So those your bones break. So she broke like her shoulder, and she had, my teacher said she never went hunting with anybody. So, oh yeah, I'm sure you did.
How is doing it more?
Like you just,
Like,
so like she was just like this against the tree,
Oh.
and then all that force went in and just the gun kept going really and just pushed through the bone and cracked, broke the bone. All right. Me neither.
Say. So I know what
Did you like restart it?
No, I don't think he did.
Might be. There you go.
There we go. Oh, well, that's the best thing. Period.
I love that hair.
Just popcorn hair
So that's Isaac Newton.
wearing with a mallet. Long. I was really, because I thought I was gonna get like a 9, 70.
So let's review the Newton's three laws in the last few minutes, now that we can see it. So Newton's first law. Someone raise your hand, describe Newton's first law to me. Come on. Yeah, an object at rest will stay at rest An object in motion will stay in motion, and when it's in motion, it's gonna stay with the same speed and direction. So same velocity, unless acted on by an outside force. So that's inertia. Object rest stays at rest, law of inertia. So that's the definition or the description. Is there a math expression for it? No. There's no math expression for the first law. That's just a law, it's a description, that's what happens. Things like to do what they're doing. Someone give me an example. Dean.
Something sitting on something like an object on a table.
Okay, so this ball sitting on this table,
Yeah.
wants to keep sitting on this table, once I push it, it's gonna roll. What if it rolls off? What's it gonna wanna do?
Fall.
Fall until when?
It's
Which is the outside force. So book sitting on a table, outside forces, friction, stuff like that. Newton's second law. Someone give me that description. Send it to you. Someone who hasn't risen. Caleb? It's Newton's second law.
It's like mass times acceleration.
So there's a description of it. Where's the description? Olivia? Yeah. The greater the mass of an object, the harder it is to move, the more force required to move it or change its movement. Taylor, what's the math expression?
Force equals mass times acceleration.
Yeah, F equals ma. Gravity, is that a force? Yeah. Your weight is due to the force of gravity. It's your mass times the acceleration of gravity. And there's a special equation in that. We'll talk about that tomorrow. In F equals ma, there's actually a special version of that equation just for gravity. What's an example? Somebody give me an example. Brian. Try and push your car. Versus like a van or a bus. So you might be able to push your car. You run out of gas, would you be able to push a bus?
Definitely.
Probably not. It might take the entire, lacrosse team.
I can do it.
So a lot of force is needed to push a heavy wheelbarrow, a lot of force is needed to push a bus. You don't have to use that example if you want to put one on your own, that's fine. This is just an example, but write down an example. Oh. Number 3, law number 3. Katie.
Every action has equal opposite reaction, or every force has
Yep. Equal and opposite reactions, equal opposite forces. There's no equation for this. There's no mathematical expression. Besides saying the force on F of 1 equals F of 2. Right? That'd be the only equation, but you don't have to write that down. That's intuitive and saying equal and opposite. Except force is in the values are equal, but what's not equal? Come on. Well, that would be because of law number 2, but if the forces are equal, the value of the force, 20 newtons, what's going to be different? The direction. Okay. After class, Priscilla, go to attendance. Good. So the direction would be different. They're going to be exactly opposite. So when you push on a wall, it pushes back on you. Bless you.
Thank you.
Another example would be like the carts we did yesterday. Sitting on a desk. If I sit on this desk, am I putting a force on the desk? Yeah. I weigh, I'm not going to tell you how much I weigh. Let's say I weigh 100 pounds. That's my force I'm putting on the desk. How much force is the desk putting on me? 100 pounds. What direction? up. Because what my direction I'm putting on the desk is down. If it didn't put 100 newtons of force, it put less than 100 newtons of force, what would happen?
You go through.
I'd go like through it. What if it pushed more?
And you go.
Then I'd be like floating up, yeah. Does that ever happen?
No.
No.
Equal space.
That'd be
This is called a
cool.
triple.
Yeah.
That'd be cool.